Hello, my name is Paul Grogan. This talk is Risk Dominance as a Decision Criterion in Collective System Design. This work studies trade-offs that are inherent for collaborative architectures. For example, in the space systems domain, there's a key trade-off right now between independent architectures, where one organization fields all of the infrastructure necessary for a mission, versus collaborative architectures, where organizations share resources during mission operations. Collaborative architectures have the possibility of being more efficient. However, they're also susceptible to downside risks if partners drop out. In this work, we want to understand how to measure these strategic sources of risk in collaborative systems that specifically account for interactive effects between decision makers. And we propose a decision criterion that can be used for trade space exploration. We frame the problem starting from a stag hunt game, where two hunters have two different strategy alternatives. They can either pursue a hare hunting strategy, which allows them to act independently to achieve a relatively modest payoff, or a stag hunting strategy, which is a collaborative strategy that yields a much higher payoff, but only if both hunters pursue this option. If we represent this game as a normal form, in its normal form seen below, we can quickly identify that there are two Nash equilibriums in this problem. Both the hare-hare and the stag-stag options are stable from an equilibrium perspective. However, equilibrium selection does not help us choose among these two equilibria. To help make selections between equilibria, we can rely on metrics or concepts such as risk dominance. To understand risk dominance, we can look, for example, at a probability space of our partner's probability of selecting the stag option, ranging between 0 if they always choose hare to 1 if they always choose a stag strategy. On this probability space, we can evaluate the expected value of our own strategies. For example, the hare hunting strategy achieves between 2 and 3 units of utility, where the stag hunting strategy achieves between 0 and 4. We can see, for example, these two strategies intersect, and that intersection point delineates what is the point in probability space that separates the hare hunting strategy as being dominant from the stag hunting strategy as being dominant. This crossover point in game theory is called the normalized deviation loss, and in this example problem, it's equal to 2/3. You can think of that as the minimum probability of collaboration required for you to choose the collaborative alternative. Reinhart-Selten formalized this risk dominance concept in a scalar measure in 1995. The measure indicates which of the two equilibria are considered risk dominant as a desirable property, similar to payoff dominance. And furthermore, this metric can be used for normative decisions under certain conditions. For a two-player symmetric case, as the stag hunt example, it has a very simple form. It's essentially just the logit of the normalized deviation loss, where positive numbers indicate the hare hunting equilibrium is risk dominant, and negative values indicate the stag hunting equilibrium is risk dominant. So for this example that we've been looking at with the normalized deviation loss of 2/3, it corresponds to a risk dominance measure of about 0.7, indicating the hare hunting equilibrium is risk dominant. And we can observe that, yes, we would prefer all other things being equal, an equal chance of between 2 and 3 units of utility versus between 0 and 4. Risk dominance is really useful for helping compare different design concepts against each other. So in this extended trade space, consider 4 different alternatives for your hunting implement or hunting weapon to be used in one of the two strategies. The 4 designs listed here are addle, bow, club, and dog, and they're evaluated in each of the 4 strategic contexts in which they might be used. Our baseline case selected dogs to be used in the hare hunting strategy and the addle to be used in the stag hunting strategy. However, we could look at different alternatives for this lower level design decision. For example, if we were to choose dogs to also hunt stag, it would be a relatively poor option because dogs do not give very high utility in that strategic context. And even in that case, the risk dominant score is not defined because this is no longer a stag hunt game. However, if we were to instead use clubs to hunt the stags, we see a moderate decrease in upside potential of the stag hunt. But we also do see some reinforcing effect of limiting downside losses. However, weighing these two factors gives a resulting risk dominant score that's even higher than our original risk dominant score of 0.7. Looking at the bow as another alternative, however, we can see that the upside potential is not quite as high as the addle-addle, but it does limit the downside losses of a failed stag hunt. And the bow option for the stag hunt strategy gives us a much lower risk dominance score, which in this case is 0. So if we frame these lower level decisions as a design trade space, we can start to think about using risk dominance as a criterion for decision making in a trade space. Here I've plotted risk dominance on the x-axis and the upside potential payoff on the y-axis. And we can see the formation of a Pareto efficient frontier of payoff risk dominant dominating solutions. We can see, for example, the payoff maximizing solution of the addle-addle, which we previously identified. We can also see the dominated solutions, such as the club, which do not provide desirable dynamics. But we can also identify some new risk competitive solutions that don't quite give as much upside potential, but do mitigate some of the downside loss in a way that might be of interest to stakeholders. So in summary, risk dominance helps to check some of the optimism biases that may be present in collective design decision making, and we propose that it helps to mitigate some of the robust yet fragile or gold-plated solutions that may result from these optimistic design decision making activities. Calculating risk dominance does depend or does rely on global visibility of the payoff values, but it is generally compatible with expected utility, risk aversion, and is extensible to asymmetric and multiplayer games. The risk dominance measure is normative, but only under very specific conditions that are unlikely to hold in practice. And in this case, we propose using risk dominance as a relative measure to help inform design decision making in trade space exploration. We'd like to acknowledge our sponsors for this work, and you can find much more information about this in our Design Science article. Thank you.